So we know the shapes of our sine and cosine parent functions. Now let's talk about transformations of these graphs. Notice, here is going to be the standard form of a sine function. Y equals a times the sine of b times the quantity x minus c plus d. Here is the standard form of our cosine function. Y equals a times the cosine of b times the quantity x minus c plus d. Notice that x and y, those are our variables, and a, b, c, and d, those are the constants that are going to define any particular transformations. Now, the transformations that we learned earlier on the year are still going to apply. You may recall what this constant multiple in front of a parent function does. A gives our graph a vertical stretch or shrink. Now, with our sine and cosine functions, this has a specific change. It influences what is known as the amplitude of our function. Amplitude refers to how far above and below the midline the wave will travel. And the midline of the graph is simply the horizontal line that goes through the middle of our sine or cosine function, okay? That goes through the middle of our trig function, and the midline for each one of our parent functions is just the x-axis, right? It splits that graph right down the middle. One thing to make note of, if a is negative, there is a reflection in the x-axis as well. So, a determines the amplitude. To find the amplitude of the function, and this is how I will phrase the question, determine the amplitude, we need to take the absolute value of a. Again, that tells us how far above and below the midline our wave is going to travel. If we are given a graph and we can see where the maximum and minimum values of the graph occur, we can find amplitude by taking the maximum value, subtracting the minimum value, and dividing it by 2. Next, let's talk about the constant b. B is a constant multiple inside of the parent function. That gives us horizontal stretches and shrinks, and those also have a special name when we're talking about our trigonometric functions. All right, we say that b affects the period. It's going to change how quickly the function repeats itself. Remember, period is how long it takes for the function to repeat. Therefore, b shrinking or stretching horizontally will change the period. If b is negative, then there is a reflection in the y-axis. I will ask you to identify the period of these functions, and to do so, period is equal to 2 pi divided by the absolute value of b. That gives us the period. Okay, period is a magnitude. It's always going to be positive. Keep that in mind. All right, c. C, what does the constant c do in each one of these functions? That gives us our horizontal shift. And with our trig functions, this also has a special name. Our horizontal shift is known as a phase shift. The parent function will be shifted horizontally c units. For trigonometric functions, this is known as a phase shift. So identifying what the value of c is will give us our horizontal shift. And finally, d. D gives us our vertical shift. The parent function will be shifted vertically d units. If d is positive, it's going to shift up. If d is negative, it is going to shift down. All right, so what we're going to want to do is make sure we can identify each one of these constants, find the amplitude, the period, the phase shift, vertical shifts, and any other transformations from our parent function. These are your guidelines for sketching sine and cosine curves. Number 1, determine the amplitude, period, phase shift, and any other transformations from the parent function. 2, begin with the shape of the parent function and include at least 2 full periods. 3, apply vertical stretches / shrinks, label the y-axis to match the amplitude of our function. You'll see what that means coming up. 4, apply your horizontal stretches and shrinks. We're going to change our period. Label the x-axis to match the period. It is helpful to use quarter period increments in your scale. All right? You'll notice I'm going to use quarter period increments whenever I'm graphing sine and cosine functions. Those will be where my tick marks are on my x-axis. 5, reflect the graph over the x-axis and or y-axis as necessary. And 6, apply the phase shift and or vertical shift. You might recall this step process from earlier on in the year. We want to do our scalings first, then reflect, and then shift. That is exactly what we're going to do. Same process, just now with our sine and cosine functions. Let's give it a go. Determine the amplitude, period, phase shift, and any other transformations from the parent function. Sketch the graph, include at least 2 full periods. Identify the domain and range of the function. All right, so f of x is equal to 3 times the sine of the quantity 2x plus pi over 2. Now, it's important to recognize we want to be able to identify each of these constants, a, b, c, and d. Notice that b is the constant multiple in front of x, but b is identified when it is factored out from these two terms with the x and the term with the c. That means what we want to do is we want to factor out a 2 and apply another parentheses in here. Doing so gives us 3 times the sine of 2 parentheses x plus pi over 4. And the reason we want to do that is because b is going to help us in determining our period, and c, now that it is alone, will help us in determining our phase shift. If you're wondering where these numbers came from, when you factor out, you're essentially dividing out that term from in front. Notice if I took 2x and divided by 2, I'd be left with a 1x. If I take pi over 2 and I divide it by 2, I pull that 2 out, I get pi over 4, right? And if I were to distribute this back in, 2x plus 2 pi over 4, well, that would give me 2x plus pi over 2. So these are equivalent expressions. We have just factored out that b constant multiple in this case. All right, so now it's in our standard form. Let's identify the amplitude. Well, how do we find the amplitude? Amplitude is the absolute value of a. That means our amplitude is 3. Our wave is going to travel 3 units above the midline and 3 units below the midline. Period. To find the period of our sine and cosine functions, we take 2 pi divided by the b constant. The b constant here is 2. 2 pi divided by 2 is equal to pi. Next, we want to identify our phase shift. This is our horizontal shift, and the phase shift is given by the constant c. One thing to make note of is that in the standard form, it's minus c. So if I have a plus sign here, that means c must be negative. C is negative pi over 4. Therefore, our phase shift or horizontal shift is pi over 4 units to the left. Other transformations. Any other transformations that we're missing? Nope, that's all of them. Okay, so what we want to do, we start with the shape of our parent function. Here is our sine parent function. Remember, the order we follow is scale, reflect, and shift. And here's what I find is the best way to do it. Number 1, start off just by clearing out all of your axes. Okay, because at the end of the day, our graph should definitely be a wave. The only things that are going to change are our labels on the axis. All right, so let's start with our vertical scalings. Let's change our amplitude. Because the amplitude is 3, that means we need to go 3 units above the midline and 3 units below the midline. We can easily do this by just relabeling our y-axis as a 3 there and a negative 3 down here. There's our vertical scaling. Now let's do our horizontal scaling. That's our period change. Well, this function is repeating itself every pi. That means when I go from here to here, that has to be pi units. Similarly, as I go in the opposite direction, 1 complete cycle, that brings me to negative pi, which means that each of these quarter period increments are going to be 1/4 of pi. 1/4 of pi, 2/4 of pi, 3/4 of pi, so on and so forth. Okay, there is our horizontal scaling. So we have done all of our scaling. Next, reflect. Well, we don't have any reflections to worry about, so we can move on to our shifts. Let's start with our phase shift. Okay, phase shift. Well, we don't have a vertical shift, so we only have to do our phase shift. This means every single point on our graph is going to shift to the left pi over 4 units. And that means that this maximum, that's at pi over 4, is going to move here, right? This midline crossing is going to move to the left pi over 4. This minimum is going to move to the left pi over 4 units. Every single point on our graph is moving to the left pi over 4 units, giving us our final graph of our sine function f of x. Now, what about the domain? The domain of every single sine function is always going to be all real numbers, negative infinity to infinity. The range, in this case, as we can see from the graph, is going to be from -3 to 3. Let's now try another one. Same thing. F of x is equal to 1 minus the sine of pi over 3x. Well, first thing we want to do is we want to put this in standard form. Notice in this case that our d constant has actually been put in front just to make the first term positive. All right, you might find it helpful to rewrite it so that we have negative sine pi over 3x plus 1. Okay, might be easier to recognize that this plus 1 is going to be our d constant. All right, so what is our amplitude? Well, amplitude is the absolute value of a. What's the number that we have in front of sine? It's a -1. Therefore, our amplitude is going to be 1. Our wave height is going to go 1 unit above the midline, 1 unit below the midline. Period. To calculate period, we have 2 pi divided by the b constant. B is the constant multiple in front of the x. Now notice in this case, I didn't have to factor anything out because there was no phase shift happening in this graph. Okay, so our period is 2 pi divided by pi over 3. And remember that dividing by pi over 3 is the same as multiplying by 3 over pi. Our pi's are going to cancel out and we will be left with 6. This will repeat itself every 6 units. Our phase shift, well, that's determined by c, which in this case, c is actually 0. There is no phase shift. And are there any other transformations? Yeah, 2 other ones. 1, notice that a is negative. That means we have a reflection in the x-axis, and also we have a plus 1 on the end. That's going to give us a vertical shift. Once we have identified all of these transformations, we start with the shape of our parent function, and remember, we are going to scale, reflect, and then shift. So, start with our wave, clear out your axes, let's relabel them, okay? Starting with our amplitude. Our amplitude is 1. That means we must travel 1 unit above the midline, 1 unit below the midline. Again, midline is just the line that goes through the middle of the graph, which for these parent functions is always the x-axis. The midline will only change if there is a vertical shift. We'll see that coming up a little bit later on. Okay, so that means that this maximum value here has to be 1, and this minimum value here has to be -1 to give us an amplitude of 1. There is our vertical scaling. Now let's do our horizontal scaling. That's going to be our period change. Well, this one complete cycle is our period. If the period here is 6, I can label this hash mark right here as a 6, which means that if I go the opposite direction, this point right here would be -6. All right? And if this is 6 and that's -6, well, halfway in between 6 and 0 would be a 3. -3 over here. Those would be 1.5 unit increments. Again, always helpful to have quarter periods. All right. We did our vertical scaling. We did our horizontal scaling. Next, we want to reflect. We have a reflection in the x-axis. So we're going to take this graph and reflect it over the x-axis. That means that every single one of these maximum values is going to become a minimum value, and every single minimum value will become a maximum value. We flip that right over the x-axis. Okay. Now that we've done our reflections, let's do our shifts. Well, we don't have any horizontal shift. There is no phase shift to worry about. We just have a vertical shift, which means we're going to take every single one of these points and shift it up 1 unit. That means that these maximums are going to move up to 1, and that these minimums are going to move up to 0, giving us our final graph. Here we have f of x equals 1 minus sine pi over 3x. All right, so what's our domain? The domain of every single sine and cosine function is always going to be all real numbers. That's a freebie point right there. Make sure you get that one. What about the range? Well, based off of our graph, we see that it crosses or hits the x-axis here. Y equals 0 is our lowest value. Our greatest y value is 2. Therefore, our range is from 0 to